Welcome to our comprehensive overview of carbon sequestration. Today, we'll explore how carbon dioxide, a major greenhouse gas, is captured and stored to help combat climate change. Carbon sequestration involves a range of natural, physical, and human-induced processes and technologies, all designed to keep CO2 out of the atmosphere. Whether through forests, oceans, or advanced engineering, these methods play a crucial role in offsetting emissions from sources like deforestation, wildfires, and especially the burning of fossil fuels. Let's begin by understanding why carbon sequestration is so important and how it fits into the broader picture of climate action. Carbon sequestration is the process of capturing and storing carbon dioxide away from the atmosphere. Sometimes referred to as carbon capture, this process helps offset the addition of CO2 from various sources. These sources include natural events like forest fires and human activities such as burning fossil fuels. By removing CO2 from the air and storing it in plants, soil, oceans, or underground, we can help slow down the pace of climate change. The goal is to balance the carbon cycle and reduce the greenhouse effect that leads to global warming. CO2 emissions are the largest contributor to greenhouse gases both in the United States and globally. While other gases like methane and nitrous oxide also play a role, carbon dioxide remains the primary focus due to its abundance and impact. Understanding the sources and scale of CO2 emissions is essential for developing effective carbon management strategies. By analyzing emissions data, we can identify key sectors and activities that need targeted interventions, paving the way for more efficient carbon reduction and sequestration efforts. There are several technological options for managing carbon emissions. First, we can reduce the carbon intensity of energy sources by switching to renewables. Second, improving energy efficiency across industries helps lower overall emissions. Third, reducing the level of high-emission activities can make a significant difference. Finally, carbon sequestration itself, capturing what's left, remains a vital tool. Each approach has its own strengths and challenges, but together, they form a comprehensive strategy for tackling CO2 emissions. Carbon sequestration methods can be divided into natural processes and human techniques. Natural processes include terrestrial sequestration, where plants and soils absorb CO2, and ocean sequestration, where marine life and water bodies play a role. On the other hand, human techniques involve advanced technologies like carbon capture and storage (CCS), which physically trap and store CO2 underground. Both approaches are necessary for a balanced and effective carbon management strategy. Terrestrial sequestration relies on the natural ability of plants to absorb CO2 through photosynthesis. When plants die, some of the carbon is transferred to the soil as roots and leaves decompose, while some is released back into the air. The rate at which plants absorb CO2 depends on factors like species, climate, soil type, and management practices. Scientists use tools like infrared gas analyzers to measure how much CO2 is taken up by plants, helping us understand and optimize this process. Uptake rate of CO2 in plants can be measured experimentally. Scientists use devices like the infrared gas analyzer, IRGA, to compare the CO2 concentration inside a chamber around a leaf with the CO2 leaving the chamber. This allows for precise measurement of how much carbon a plant absorbs. Such data is crucial for understanding the effectiveness of different plant species and management practices in sequestering carbon. Carbon accumulation in plants doesn't continue forever. Eventually, plants reach a saturation point after which they can't sequester more carbon. For trees, this happens when they mature or when the soil's organic carbon becomes a limiting factor. This concept is important because it means that simply planting more trees isn't always the answer. Management and species selection matter too. Rate at which trees sequester carbon depends on several factors. These include the species of tree, the conditions where it's planted, and the density of its wood. Most research has focused on temperate tree species, and results can vary widely depending on the region. Understanding these variables helps scientists and land managers make better decisions about which trees to plant and how to manage forests for maximum carbon uptake. Estimate how much carbon a tree can sequester. We start by determining its green mass, the weight of the tree when it's alive. This involves measuring the trunk's diameter and the tree's height. For smaller trees, a specific formula is used, while larger trees require a slightly different calculation. The root system is also considered, as it adds about 20% to the above-ground mass. These calculations provide a baseline for understanding a tree's carbon storage potential. Next, we determine the dry mass of the tree. The dry mass is the green mass minus the water content, which varies by species. On average, trees are about 72.5% dry matter and 27.5% moisture. This step is important because only the dry portion of the tree contains carbon that can be sequestered long-term. After finding the dry mass, we estimate the mass of carbon in the tree. Studies show that trees are typically about 45% to 50% carbon by dry weight. For calculation purposes, multiplying the dry mass by 50% gives a good estimate of the carbon content. This step helps us understand how much carbon is actually being stored in the tree's structure. To convert the mass of carbon in a tree to the mass of carbon dioxide sequestered, we use a simple ratio based on molecular weights. Since CO2 is heavier than carbon alone, we multiply the carbon mass by 3.667. This gives us the total amount of CO2 that the tree has removed from the atmosphere and stored in its tissues. Scale up from a single tree to a whole forest, we consider tree density, how many trees are planted per acre. Using formulas for tree spacing and area, we can estimate the total number of trees and therefore the total carbon dioxide sequestered per acre. This approach helps land managers and policymakers plan large-scale reforestation and carbon offset projects. Average annual sequestration rate is calculated by dividing the total mass of carbon dioxide per acre by the average age of the trees. While the actual rate can vary over large areas and many trees, the sequestration rate tends to be fairly consistent. This information is vital for understanding the long-term impact of forests on atmospheric CO2 levels. Let's look at some real-world examples. A 10-year-old Grevillea robusta, 45 feet tall with a 6-inch trunk, sequesters about 3.7 metric tons of CO2 per acre per year. A 2.5-year-old Acacia angustissima, 15 feet tall with a 3-inch trunk, sequesters 3.42 metric tons per acre per year. And a 15-year-old Albizia lebec, 30 feet tall with a 12-inch trunk, sequesters 3.94 metric tons per acre per year. These examples show how species age and spacing all influence sequestration rates. Peatlands or peat bogs are a unique type of wetland that cover about 3% of the world's land area. These areas trap organic material before it can fully decay, locking carbon underground for thousands of years. Peat bogs are the largest natural terrestrial carbon store, sequestering more CO2 annually than all other biomass combined. Protecting and restoring peatlands is a powerful way to enhance natural carbon sequestration. Agriculture can play a big role in carbon sequestration. By planting cover crops between growing seasons, farmers can increase biomass and trap more carbon in the soil. Rotational grazing, where livestock are moved between paddocks, encourages deeper root growth and healthier soil. Restoring degraded land through reforestation, afforestation, and wetland restoration also helps slow carbon release and boost sequestration. Forestation involves replanting trees in areas that were previously forested, while afforestation means planting trees in areas that never had forests before. Both strategies increase biomass and enhance carbon uptake. These efforts are especially important on marginal lands such as old crop fields or pastures, where new forests can thrive and store significant amounts of carbon. Storing wetlands is another effective way to trap carbon. Wetlands store 20–30% of the world's soil carbon, even though they make up only a small portion of the land surface. Coastal wetlands like mangroves, seagrasses, and salt marshes are particularly important. By re-establishing or rehabilitating these ecosystems, we can promote carbon trapping in the underlying sediments and help mitigate climate change. World's oceans are massive carbon sinks, holding about 38,000 gigatons of carbon, 16 times more than all terrestrial biomass. Oceans absorb CO2 from the atmosphere where it is used by marine life or stored in deep water and sediments. This natural process is a critical part of the global carbon cycle and helps regulate the Earth's climate. Near the ocean's surface, plankton use photosynthesis to convert CO2 into sugars. These plankton are then eaten by sea creatures, moving the carbon through the marine food web. When marine organisms die, their bodies sink to the ocean floor where the carbon is stored in sediments for thousands of years. This process keeps carbon out of the atmosphere for long periods, making the ocean a powerful carbon sink. Carbon stored in deep ocean sediments has a very long residence time, often thousands of years. This means that once carbon reaches the deep ocean, it is effectively locked away from the atmosphere for millennia. The slow exchange between deep ocean water and the surface ensures that this carbon remains sequestered, helping to stabilize global CO2 levels. Marine animals like plankton and whales play a surprising role in ocean carbon sequestration. For example, sperm whales help transport iron from the deep ocean to the surface, which stimulates phytoplankton growth. More phytoplankton means more carbon is absorbed from the atmosphere. The decline in whale populations due to whaling has actually reduced the ocean's ability to sequester carbon, showing how interconnected life and climate are. Seaweed, which grows in shallow coastal areas, is another natural tool for carbon sequestration. Through photosynthesis, seaweed captures significant amounts of CO2, which can later be transported to the deep ocean as the plants die and sink. This process mimics the natural sedimentation pathway and helps lock carbon away for long periods. Scientists have explored ways to enhance ocean sequestration by adding nutrients like iron or urea to the water. The idea is to stimulate phytoplankton growth, which would absorb more CO2. However, these techniques are controversial due to potential side effects on marine ecosystems. Ongoing research continues to evaluate the risks and benefits of ocean fertilization. Carbon capture and storage (CCS) is a geoengineering technology that physically prevents large amounts of CO2 from entering the atmosphere. CCS can capture up to 90% of emissions from power plants and industrial processes. The captured CO2 is then transported and stored underground, often in geological formations like depleted oil and gas fields. CCS is a promising complement to natural sequestration method. CCS technology is already used in industries like fertilizer production, chemical manufacturing, and power generation. The process starts by partially oxidizing fossil fuels to create syngas, which is then converted into CO2 and hydrogen. The CO2 is captured while the hydrogen can be used as a cleaner fuel. This approach shifts the energy carrier from carbon to hydrogen, reducing emissions before combustion even occurs. Post-combustion capture, CO2 is removed from exhaust gases after fossil fuels are burned. The challenge is separating CO2 from other gases like nitrogen and oxygen. This is done by treating the flue gas to remove impurities, then using a liquid solvent, usually an amine solution, to absorb the CO2. While effective, this process requires extra energy, which can reduce the overall efficiency of power generation. Oxyfuel combustion burns fossil fuels and pure oxygen instead of air, resulting in exhaust gases with a much higher concentration of CO2. This makes it easier to capture the CO2, but the process creates very high flame temperatures, requiring cooling systems and recirculation loops. While sometimes called a zero-emission cycle, it's important to treat water vapor in the exhaust to ensure all CO2 is captured. Once CO2 is captured, it's transported and injected into underground geological formations. Good storage sites include saline formations, depleted oil and gas reservoirs, and unminable coal seams. The goal is to trap CO2 securely, preventing it from leaking back into the atmosphere. This long-term storage is essential for the effectiveness of CCS. There are several ways CO2 can be trapped underground. Structural trapping places CO2 beneath a dome of impermeable rock. Residual trapping locks CO2 in the pore spaces of rocks. Solubility trapping occurs when CO2 dissolves in brine water, while mineral trapping involves chemical reactions that bind CO2 to minerals. Each mechanism adds a layer of security to underground storage. Some of the captured CO2 can be used for enhanced oil recovery. In this process, CO2 is pumped into depleted oil reservoirs, pushing remaining oil to the surface. The CO2 stays underground, taking the place of the extracted oil. This technique not only increases oil production but also stores CO2 securely underground. While CCS offers great promise, it also faces challenges. These include the high cost of technology, the need for suitable geological sites, and the energy required for capture and storage. However, ongoing research and policy support are helping to overcome these barriers, making CCS an increasingly viable option for large-scale carbon management. Most effective carbon sequestration strategies combine natural processes with human technologies. By protecting forests, restoring wetlands, and deploying CCS, we can address emissions from multiple sources. This integrated approach maximizes our ability to reduce atmospheric CO2 and slow climate change. Governments and international organizations play a key role in advancing carbon sequestration. Policies that support research, incentivize reforestation, and fund CCS projects are essential for scaling up these solutions. Global cooperation ensures that best practices are shared and implemented worldwide. Looking ahead, innovation will drive the future of carbon sequestration. New technologies, improved land management, and greater understanding of natural processes will all contribute to more effective carbon capture and storage. As we continue to learn and adapt, carbon sequestration will remain a cornerstone of climate action. Community involvement is crucial for successful carbon sequestration projects. Local knowledge, participation, and stewardship help ensure that projects are sustainable and beneficial for both people and the environment. Educational programs and outreach can inspire more communities to take action. Accurate monitoring and verification are essential for tracking the effectiveness of carbon sequestration. Technologies like remote sensing, satellite imagery, and on-the-ground measurements help ensure that carbon is being captured and stored as intended. Transparent reporting builds trust and accountability. Carbon sequestration can provide economic benefits, too. Reforestation and wetland restoration create jobs, support local economies, and enhance ecosystem services like water purification and flood control. CCS projects can also drive innovation and investment in clean energy sectors. Despite its promise, carbon sequestration comes with risks. Improperly managed projects can lead to unintended consequences, such as ecosystem disruption or CO2 leakage. Careful planning, ongoing research, and adaptive management are necessary to minimize these risks and maximize benefits. Building public awareness and support is key to advancing carbon sequestration. Clear communication about the benefits, challenges, and opportunities helps foster understanding and engagement. When people are informed, they are more likely to support policies and participate in local projects. Around the world, there are many success stories in carbon sequestration. From large-scale reforestation in Asia to innovative CCS projects in North America, these examples show what's possible when science, policy, and community come together. Learning from these successes can inspire new projects and drive further progress. To sum up, carbon sequestration is a vital tool in the fight against climate change. By combining natural processes with advanced technologies, we can capture and store significant amounts of CO2. Ongoing research, policy support, and community engagement will ensure that these efforts continue to grow and succeed. As we look to the future, the importance of carbon sequestration will only increase. With continued innovation, collaboration, and commitment, we can make meaningful progress toward a more sustainable and climate-resilient world. Thank you for joining us on this journey through the science and solutions of carbon sequestration.